Okay, welcome to Introduction to Photonics. Good morning. We've been discussing the nonlinear response of materials to electromagnetic waves, in this case optical waves. And in the previous lecture, we were looking at the third order susceptibility. The one before that we were looking at second order susceptibility, but in the last lecture we were looking at third order susceptibility, and we were discussing all the possible phenomena that can happen when you have a material with relatively high third order susceptibility. There's one question as to, when do we see chi2 related effects and when do we see chi3 related effects? Can both of those happen in the same medium? Yes, it can. Everything depends on the relative values of chi2 and chi3, but we don't have any control on the response itself. That is the medium property. The only thing that we can provide is the electric field, the excitation, right? So we were talking about four-way mixing. We were talking about self-phase modulation through the nonlinear Kerr effect, and we stopped at this point where we were talking about self-phase modulation in a long length of fiber. We were saying that depending upon the intensity of the light, the medium responds differently, and so it essentially ends up delaying some part of the pulse with respect to others, and that delay essentially is it produces new frequencies that were previously not present in the pulse spectrum. So these new frequencies, we essentially call these as chirp. So what that chirp also does is that the delay it's a positive slope with respect to the frequency, and we were discussing the aspect that this could actually be good in the sense that this could potentially compensate for the dispersion in a medium, and so you could have the pulse retaining its shape as it propagates down the fiber, which would be very good for optical communication systems because you don't incur these dispersion related penalties, which is actually causing bit error rates in your communication system. And I should mention that there is one particular shape of the pulse, okay, in which the self-phase modulation that it incurs and the chirp that it incurs automatically compensates for the dispersion that the pulse incurs, and you can remain that shape all along the length of the fiber. So effectively what we are saying is the propagation inside this medium is controlled by what is called the nonlinear Schrodinger wave equation. So it's just a nonlinear Schrodinger wave equation it's just a modification of the regular wave equation that we've been looking at, but it brings out the nonlinear aspects clearly. So if you take the nonlinear Schrodinger wave equation and you find the solution for the nonlinear Schrodinger wave equation, you find that a pulse which has actually a secant square, secant hyperbolic square sort of shape is actually is a solution for this Schrodinger wave equation, which means that that shape pulse, if you send it down a regular single mode fiber, you will actually retain that shape, okay, and that sort of pulse is called a soliton. So a soliton is essentially a solution for the nonlinear Schrodinger wave equation, is such that dispersion and this nonlinear chirp, it's automatically compensated, so it retains its shape all along its the propagation. And in fact, back in the 90s, there was a lot of research on soliton pulses. So people figured if you use soliton pulses, you don't have any of these dispersion related penalties. So they said, okay, this is the way to do communication. But of course, there were other issues with the propagation of solitons. When you talk about practical, things that are happening in the field, there were a lot of issues with solitons, and people actually gave up on that idea after a while. But that's just for your information. So what we do now in communication systems, and this is what you learn if you take this fiber optic communication technology course, is that you let dispersion to happen in the fiber up to say some 100 kilometers, and then you have a dispersion compensation element which brings the shape back to its original shape, pulse shape, and then it's allowed to go further down, accumulate dispersion, then dispersion compensation, and so on. So that's what we call as a dispersion managed system. That's what is practically implemented in modern day communication systems. Okay, so let us actually take a look at this in a slightly deeper manner. Let's actually try to quantify what is the nonlinear phase that you accumulate while propagating down the fiber. Okay, so to look at that, what we have to consider is that nonlinear phase you have one value if you consider the power to be uniform along the length of the fiber, but we know that is not possible because the fiber does have loss. So the power is actually exponentially decaying along the length of the fiber, right? So if you look at the power that's propagating through the fiber, we know that it's going to be exponentially decaying. Of course, it is not probably very strong exponential decay, because alpha tends to be very small. Alpha is 0.2 dB per kilometer, right, typically for a communication grade single mode fiber. Nevertheless, we do have to, when we are talking about the nonlinear phase that's accumulated, we do have to consider the fact that the phase that's that you have at any particular section along the fiber is dependent on the power at that particular point, right? So if you want to look at the accumulation of phase, you have to integrate over all those power levels. So this is going to be 2 pi over lambda multiplied by n2 divided by a, and then we were just previously considering the power, but now we are talking about phase accumulation along the entire length of fiber. So you say P of z dz with your limit going from 0 to L, where L is the total length of this fiber. right? So that's the total phase that's accumulated. Now of course you say P of z is P naught multiplied by e power minus alpha z. So you can write this as 2 pi over lambda multiplied by n2 divided by a, and if you do that integral you get P naught multiply this by this factor e power minus alpha L divided by alpha, right? That's what you get when you integrate e power minus alpha z. Okay. So previously when we were looking at the phase, we were saying 2 pi over lambda n2 over a, power multiplied by length, right? Now instead of length we are actually having this thing in the parenthesis. So this is actually denoting an effective length, right? So what does that effective length mean? Well, physically what it means is that the power is it's going down over a certain length. So beyond a certain length the power is so small that the medium starts behaving linearly, right? Beyond this length the power is so small that the medium is starting to behave linearly. So even if you have length longer than that, there is no extra nonlinear phase that's accumulated. You understand this? Right? So the nonlinear phase actually depends on the intensity. That's what the Kerr effect is, right? And for a given effective area for the mode, it depends on the power, right? If you're talking about a single mode fiber. So and the power is decreasing along the length of the fiber. So if you go to such a length that the power has decreased to, let's say, something in the order of 100 microwatts or lesser than that, then you don't accumulate any nonlinear phase. The intensity is so low that you don't accumulate any nonlinear phase. You accumulate only the phase due to this n naught term. You don't have this n2i term come into the picture because that is negligible compared to n naught. Right? You understand this? That's right. You have gone to such a long distance. So if you want to compute what is L effective for a given fiber, right? Let us take the case of your regular single mode fiber. SMF 28 is a regular telecom grade single mode fiber. For SMF 28, alpha is 0.2 dB per kilometer. Okay, so that is actually if you want to convert it to Nepers per meter, how do you do that? So that's 0.2 into 10 power minus 3 dB per meter, and if you want to convert to Nepers, from dB to Nepers, you divide by 4.34, right? So you can say this is 0.2 divided by 4.34 multiplied by 10 power minus 3 Nepers per meter, right? So that is such a small value that if you consider 1 over alpha, that's the term that you have over here. If you consider 1 over alpha, that would work out to be roughly about 20 kilometers, 21.7 kilometers or something like that. Okay, so what we are saying is it's accumulating this nonlinear phase over 20 kilometers, but beyond that the power level is so low that it doesn't have any nonlinear phase that's accumulated, right? You understand this? So that's what we mean by the effective length. The physical length can be greater than 20 kilometers, but as far as figuring out the effect of figuring out the Kerr effect, the nonlinear phase that's accumulated due to the Kerr effect, you have to take only the L effect, L effective. Yeah. Okay. So let me grab this and copy. So what we are saying now is phi and L is given by this. Now this can be approximated if alpha L is far greater than 1. If alpha L is far greater than 1, or L is far greater than 1 over alpha, right, then what we find is e power minus alpha L is a negligible number, right? Then you can just represent this as 2 pi over lambda n2 over a p naught multiplied by 1 over alpha. Okay, where n2 is 10 power minus 10 centimeter square divided per watt. So you can basically write it as 10 power minus 14 meter square per watt. A corresponds to basically A effective, that's the effective mode area in the fiber, which we said is 50 micron square. Okay, let's consider a lambda of 1.5 micron. Okay, and 1 over alpha is given by it's actually 21.7 kilometers if you do the math. Okay, so the question is, if you have 1 milliwatt of power, how much nonlinear phase do you accumulate? So if you substitute all these values, what you will find is the nonlinear phase that's accumulated is 0.58 pi. Yes. So L is far greater than 1 over alpha. Is that?
You said na ki phase will not remain nonlinear.
That's right. So beyond that it won't remain nonlinear. So you can cap it at 1 over alpha. If the physical length is greater than 21 kilometers, you can, or even if it is comparable to 20 kilometers, you can just approximate that as 1 over alpha. So we say that's the phase that's accumulated, and is that a problem? Well, maybe, because what this phase means is that you are expecting your pulse to come at a particular slot, bit slot in your digital communication system. Because of this phase, the pulse is actually moved over here, right? The pulse is moved over here, so part of the energy that's in this slot is actually showing up in the next slot. So if you are trying to make a decision whether this is a 0 or a 1, you will end up actually making an error in that, right? So there is only so much phase that you can tolerate. In fact, in communications, they say, okay, you can tolerate only up to 0.1 pi. So, fraction of a pi is all the phase that you can tolerate, and you can work backwards and say what should be P naught, what should be the power level that we transmit, so that you get only 0.58 pi. By the way, this is for P naught of 1 milliwatt. So, you have to be careful about that. So, in communications, so in optical fiber communications, the power level in the fiber, right, P is typically less than 1 milliwatt. So, you do not try to go beyond a milliwatt in communications, because this is one of those non-linearities that can affect your communications. Okay. But there is one more thing which is also quite important to consider. There is one more nonlinear effect that can limit your power that you use for optical fiber communications. So, let us move on to that. Is there any other question related to this? Oh, by the way, so I am talking about this being a deleterious effect as far as communications is concerned, but it could be used as a beneficial effect. It could be used to our advantage in certain other applications. One example of that is in mode locking of a laser. There is actually what is known as Kerr lens mode locking that you can do. Remember, what we want to do in mode locking is that we want to lock all the longitudinal modes in phase, right. That is what we talked about several weeks ago, right. And to lock all the longitudinal modes in phase, one of the things that you will have to do is you have to essentially limit the time over which the cavity is open. So, we talked about the case in mode locking, like if you have a, let us say, a ring cavity, you essentially have a switch that opens or closes. Okay. What is the rate at which it should open or close to achieve mode locking? We talked about opening or closing at the rate of the cavity round trip frequency, right. So, you open and close at the cavity round trip frequency, so that you form a pulse, and that pulse is actually circulating within this cavity. That is what we talked about when we were discussing mode locking. So, you need a mechanism that can open and close at the cavity round trip frequency, and that mechanism could be this Kerr lens, right. So, what do we mean by the Kerr lens? Normally, let us say you have a light wave coming in, it is going through a lens, and then it is focusing at a certain point, at a certain location, right. It is coming to a focus at a certain location. Now, if this medium, if the power level that is incident on this medium, the intensity of light incident on that medium is very high, the refractive index that it actually exhibits is different, right? So if I have a light wave which has an intensity pattern like this, that's incident on the medium, then what it does is the medium responds differently, okay, and so your instead of this being focusing over here, it might actually focus here itself, okay. So this is actually what is called self focusing effect, okay, and because of that self focusing, so you essentially, if I put an aperture over here, low intensity pulses will focus over here, high intensity will focus over here. So that aperture prefers to send high intensity pulses, whereas it will block low intensity pulses. Do you understand that? If I put an aperture over here such that it allows only the self-focused light, self-focusing happens only for high intensity. So if I have a low intensity pulse, that pulse would have actually would be focusing over there, right? And there, when it's trying to get there, this aperture is blocking it. So it's actually providing a loss for low intensity pulses. So you have what is called this intensity based loss mechanism, okay. And this intensity based loss mechanism is through the Kerr effect. So that's why we call it as a Kerr lens effect, and you can use this to do mode locking, that is you can use it to shape pulses within the cavity, and so that is actually a very good mechanism for mode locking a laser, okay. It's a very popular mechanism for mode locking a laser. So I'm not doing justice to that, I'm just trying to give you some general idea, but there is a lot more detail in that you may not understand, but that's okay. I just wanted to give you a picture that it could be used for a beneficial purpose also. Okay. So we said the power is limited to milliwatt levels. The other mechanism that limits the optical power that can be sent through an optical fiber is this effect which is called stimulated Brillouin scattering. Brillouin is actually the name of a scientist who obviously did some very nice experiments to demonstrate this effect. So what really happens in this? Let's take once again the example of an optical fiber communication system. I say I want to, I'm communicating between point A to point B, right? Let's say over a distance of 100 kilometers. Now I have a new locality that's developed beyond point B. Okay, I want to stretch my communication system to reach that location. I want to put extra fiber and reach that location. What would you do if you want to do that? If you want to use the same fiber link, but I have that extra length that I want to support, so I need to, at the extra that new location, I put a receiver, and I need to be able to detect a minimum amount of power, right? So what would you do to reach that location? Huh? If you are sitting at the transmitter, you can increase the transmitted power, right? So you'd say, okay, I mean, this is the same as your antenna problem. You are supporting a certain cell with a certain amount of power. Now there is a requirement to expand the cell, so you increase the transmit power, right? That's the natural thing you would do in a communication system. But in this case, in an optical fiber communication system, let's say this is the incident power, that's the power that's launched into the fiber. As you increase your incident power, the transmitted power is also going to increase linearly, and beyond a certain point it will just saturate. So there is it basically says that I cannot go beyond a certain power level, right? Even if I put more power, it's not going through, it's like hitting a wall. I am not able to increase the transmitted power. Why is this happening? Well, this is happening because if you look at, so this is on the transmitted power, but if you look at the back reflected power, the back reflected power would be like this. So this is my reflected power. So whatever I throw into the fiber beyond a certain power level, it's just coming back to me. It's all back reflected, and that obviously does not help in a communication system, right? You are trying to send information from one end to another, but beyond a certain power level, that information is just coming back to you. It's not going through to the other end. Okay. So what is happening in this sort of case? What actually provides this threshold? And I would say that just give you a feel for this. This threshold is in the order of about 5 milliwatts, around about 5 milliwatts in a regular single mode fiber. Okay. So what exactly is happening? Well, to understand this, you need to look at what is happening when light actually propagates through a medium. In this case, let's say it's a fused silica glass medium that corresponds to an optical fiber. You are sending an electromagnetic wave into this medium, let's say at frequency nu naught. Okay. Now within this medium, you would actually find that it's consisting of atoms and molecules, and if it's a fused silica medium, it's highly amorphous in nature. So you have all these atoms that are sitting around, and then there are bonds between them, right? So it's a network, it's a glass network, right? And that network is not at room temperature, it's not static. I mean, you look at a fiber and it says a piece of solid and that's all static, right? But if you look at the microscopic picture, all these atoms are all moving around their mean positions. So there are some vibrations that entire network is getting agitated. Okay. And these vibrations are referred to as acoustic phonons. This is like even at room temperature, there are some sound waves that are generated within that optical fiber. It so happens that these sound waves are now backscattering part of the light. Okay, your light is getting scattered by these acoustic phonons. Okay, and so now part of that light, I mean, it's scattered in all directions, right? But part of that light is captured by the fiber and it's going back, and that part of that light will now interact with the incoming light, right? So the fields of the incident light and the field of the back reflected light, they interact with each other and they actually generate a periodic change in the refractive index. Okay, so that periodic change is corresponding to, so your that is through your chi3, that's actually to the imaginary part of your chi3 E total square. That E total is the incident electric field and the scattered electric field. Corresponding to that, there will be a total electric field, and that electric field will essentially cause a change in the response of the medium, change in the refractive index of the medium, and it will give you this periodic thing. That periodic grating now will reflect this even more strongly, so that you go back with a frequency that is given by nu naught minus nu b. Nu b is referred to as your Brillouin frequency. Okay, and then this entire effect is essentially called Brillouin scattering. So what are we talking about? We are talking about light getting scattered by sound waves inside this medium. Okay, these are naturally occurring sound waves inside this medium, and because of that you have a downshift in the frequency. Why is a downshift in the frequency? Well, you can say that since your light wave is propagating from left to right, right? Your sound waves are also going in that direction, but it cannot move at the speed of light. It can move only at the speed of sound. Okay, so you can say that if you are sending a pulse of light, that pulse actually travels from left to right, and correspondingly there is a scattering happening and there is an interference pattern. That interference pattern also moves from left to right in the same direction as your light wave. Okay, so what happens when you reflect off a moving object? So you have a sound wave, let's say, well, we are talking about a light wave, but I'm just giving you an analogy. If you have a sound wave echoing from a moving object, what happens? Doppler shift, right? And if it's a object that's moving away, it's a downshift in frequency. If it's coming towards you, it's an upshift in frequency. So that's the kind of frequency shift we get because this entire interaction is moving from left to right. It's actually corresponding to a downshift in the frequency, and that downshift can be quantified by considering you know what is happening in terms of the k vectors, right. So, we have an incident k vector like this, let us call this the pump k vector. Pump is basically the incident k vector, and then what you have is ks coming in the reverse direction. This is actually what is called that is the Brillouin scattered wave, and it is also, you know, the difference between the two is given by the acoustic wave vector. So, I can write an equation saying that Kp minus Ks is given by Ka. So, I have a scattered wave due to this acoustic wave, right. That's propagating the material. Now, if I say that the magnitude of Kp is approximately equal to the magnitude of Ks, and since it's actually Ks is in the opposite direction, so you can write this as 2 times magnitude of Kp is equal to the magnitude of Ka, right, because what we are saying is this both of these, the incident wave as well as the scattered wave correspond to the wavelength of light, whereas Ka corresponds to the wavelength of sound waves. Sound waves have a much longer wavelength compared to light wavelength, right, and because of that K, which is 2 pi over lambda, Ks is much greater than Ka, right. So, you can write this as Ks is almost equal to Kp, in which case you can say 2 times Kp equals to Ka, and 2 times Kp is nothing but 2 pi over lambda p. Lambda p is the wavelength corresponding to the incident wave multiplied by n effective, right, is the effective refractive index that the wave is seeing in the fiber. This equals your angular frequency, which is 2 pi nu b, right, that nu b is the frequency of the acoustic wave, divided by Va, where Va is the velocity. So, you can write this as 2 pi over lambda, where lambda corresponds to the wavelength of acoustic wave, and that wavelength is Va divided by nu b, right. So, of course, you can say in this 2 pi cancels, and so what you have is nu b is given by 2 times n effective multiplied by Va divided by lambda p. Okay. So, this is essentially the downshift in the frequency that you get to see. Okay. So, if we put some numbers to this, n effective, let us say, is approximately 1.5, right, and Va is the sound of is the velocity of sound in fused silica, which is about 6 kilometers per second, and lambda p, let us consider that to be 1.5 microns, right. If you substitute all of this, you just get nu B is 12 gigahertz. Okay. So, your scattered frequency is 12 gigahertz downshifted from the light frequency. Okay. This is what you see in silica fibers. But so that is a level of detail that may not be so interesting to some people. What is important to understand is that you have this effect where beyond a certain power level that you put into the fiber, right, you start having this Brillouin scattering, which means that light is actually getting backscattered. Okay, it's not going forward. Now, so that's actually very bad for communications, right? It's really bad for communications. But there is actually a finer point which maybe gives us some hope. That finer detail is that this is the threshold if your source is highly coherent. Okay. What do I mean by that? If my source is highly coherent, that means it's a monochromatic source, right? It has only one color. If it has one color, then I have a very specific wave pattern like this. And if I have a very specific wave pattern, then my interference fringes are very strong. Okay. If you don't have that coherence, if you say my light wave is relatively incoherent, it has got multiple frequencies to it, then you don't have a very specific wave pattern. The wave is sort of like spread out, and correspondingly when you are doing that interference, what do you get as interference for incoherent light? The fringes just wash out. You don't have these high visibility fringes. So for incoherent light, stimulated scattering, this Brillouin scattering is not a problem. And why am I calling it stimulated Brillouin scattering? Because Brillouin scattering happens at any power level. When light actually goes through the medium, it gets scattered by these acoustic phonons in the medium. Okay, but only beyond a certain power level, the scattered light is actually interacting with the incoming light and creating a grating which really enhances the backscattered light. So only beyond this sort of power level, you have that backscattering happening in a very strong manner. Okay, and in that case, it's actually stimulated. That backscattering is stimulated by your regular spontaneous scattering. Okay, so that's why it's called stimulated Brillouin scattering. But nevertheless, this is a threshold if it's highly coherent. But you need coherence in communications. Why? Narrower the line width, less will be the dispersion that you incur in your optical fiber communication system. So that's why you try to go for a highly coherent laser like a distributed feedback laser. But if you use distributed feedback laser, you better not go beyond milliwatt of power level, because beyond that you start seeing effect of stimulated Brillouin scattering. It doesn't help to keep increasing the power, because you will end up having this issue of stimulated Brillouin scattering. Okay, but I teach this other course, optical sensors, in parallel. I'm going to go to a lecture in an hour from now, and I'm going to tell them stimulated Brillouin scattering is great. Why? Because for sensing, it's actually a wonderful opportunity, primarily because of the fact that when you look at this VA, this velocity of acoustic wave, that velocity is dependent on the density of the medium, okay, and then that density changes whenever you are subjecting the fiber to strain or temperature, okay. So what does that mean? In a long section of fiber, if I have a particular section where I have strain or temperature, in that section the velocity of the acoustic wave is changing, which means that the frequency that's backscattered from that particular section is changing. So if I am tracking this frequency around 12 gigahertz, I can tell how much is the strain or temperature at that particular point. So it's bad for communication, but it could be very good for sensing applications. Okay. Okay, let me stop here.